In this video, we will focus on the software installation required for programming the platform flash. Since the onboard programmer is based on the CH341 IC, the appropriate USB driver and programming software must be installed on the PC. Both the driver and the programming utility are easily available online. Open a web browser and search for CH341A on the Robu website at robu.in. From there, you can download the required driver and programming software. Once downloaded, install the driver first, followed by the programming software, as per the installation instructions. After successful installation, connect the development board to the PC using a USB cable. The system should now recognize the CH341 device correctly. A screenshot of the CH341 programming software is shown here. Let us now move on to software testing of the platform flash programming setup. First, short jumpers J7 and J2 and then connect the board to the USB port of the PC. With this configuration, the CH341 is placed in programming mode and the FPGA is held in the reset condition, which is required for flash programming. Next, open the CH341 programming software on the PC. Click on the Detect button in the software. If the connection is correct, the manufacturer name, chip name, and memory capacity of the flash device will be automatically read and displayed by the software. A sample configuration file named toggle.bin is provided. This file contains a simple test design that toggles all the GPIO lines connected to connectors J4 and J5. Open this toggle.bin file in the programming software. Now click on the Operate option and enable the Auto Program mode. Make sure that the Erase, Blank Check, Program, and Verify options are all selected. Finally, click on the Auto button to start programming the platform flash. Once the programming process is complete, the flash memory will contain the new FPGA configuration and will be ready for operation after reset. Now, open jumper J2 to release the FPGA from the reset condition. Once the reset is released, the FPGA will automatically load the configuration file from the platform flash. Next, use jumper wires to connect the required FPGA GPIO pins to the LED connector J3. After making these connections, observe the LED indicators on the board. You should see the LED indicators toggling continuously, which confirms that the FPGA has been successfully configured and that the GPIO functionality is working as expected. Let us now move on to Verilog code development for this FPGA platform. The software used for development is Efinix, which is the design and implementation tool provided for Efinix FPGAs. Using Efinix, we can write Verilog code, synthesize the design, and generate the final .bin configuration file required for programming the platform flash. First, download and install the Efinix software, and then open the application. To begin, create a new project. Provide a suitable project name and select the desired project location on your system. Next, select the FPGA family as Trion, and choose the device T20Q144. For the timing model, select I4 which matches the device used on this development board. Now enter the top module name in the Design tab. For this example, the top module name given is LED_toggle. Once the project is created, add a new source file to the project. Create a new Verilog file named eg1.v and add it to the project. This file will contain the Verilog code used to toggle the FPGA GPIO pins, which will be demonstrated in the next steps. The Verilog program used for testing is shown here, and the file is named eg1.v. This design uses the 50 MHz clock input and divides it internally to generate a slow, visible toggling signal suitable for driving an LED. The module is named LED_toggle and has two ports, CLKIN and LED. The CLKIN input is connected to the onboard 50 MHz oscillator present on the development board. The LED output is connected to FPGA pin number 38, which is brought out on the J4 connector. An LED connected to this pin through the J4 connector will be used for visual observation. Internally, a 26-bit counter register, named count, is declared. In the always block, the counter is incremented on every rising edge of the clock input. This counter effectively acts as a clock divider, where higher-order bits toggle at much lower frequencies compared to the input clock. The LED output is directly assigned to bit 25 of the counter. As a result, this bit toggles at a very slow rate, producing a clearly visible blinking effect on the LED. Even though the input clock is running at 50 MHz, the use of the counter makes the LED blinking slow enough to be easily observed by the human eye. This simple example demonstrates clock division, basic sequential logic, and GPIO control using Verilog, making it ideal for verifying correct FPGA operation and pin connectivity. Once the Verilog code is written, the first step is to check the syntax. Efinix provides an Analyze button, which can be used to verify the Verilog code for syntax errors. Click on this button and ensure that the code analyzes successfully before proceeding further. After syntax verification, the next important step is to assign FPGA pins to the design signals. This is done using the Interface Designer tool in Efinix. Click on the Designer tool icon to open the Interface Designer. Please note that there may be a short time lag after clicking the icon before the tool window actually opens. Once the Designer tool opens, we begin by creating the clock input. In the Design Explorer, click on GPIO to select it. Then right-click and choose Create Block. In the block editor, set the instance name as CLKIN. Select the connection type as PLL_CLKIN, set the mode to input, and choose the I/O standard as 3.3 volts. Next, go to the Design pull-down menu and enable Show or Hide GPIO Resource Assigner. In the Package Pin field, enter pin number 132, which corresponds to the pin where the 50 MHz oscillator is connected on the board. Press Enter key after typing 132. Now we create the output signal for the LED. Add a new single-bit output, name it LED, and set the mode to output. For the register option, select None, and set the drive strength to 1. In the GPIO Resource Assigner, assign the package pin number 38, which corresponds to the J4 connector as per the schematic. This pin is connected to an LED through the J4 connector and will be used for the blinking experiment. Once the signal assignment is completed, save the design. At this point, the pin mapping between the Verilog design and the FPGA hardware is complete, and the project is ready for synthesis and implementation. Once the pin assignments are completed, the next step is to run synthesis. Click on the Synthesis tool icon in Efinix to start the synthesis and implementation process. After successful completion, the tool automatically generates the .hex and .bit files, which represent the compiled FPGA design. However, these files are not directly suitable for programming the platform flash. The platform flash requires the configuration data in .bin format. To perform this conversion, open the Programmer tool in Efinix. Inside the Programmer tool, load the generated .hex file. Once the file is loaded, go to the File menu and select Export, and then choose .bin as the output format. This process generates the .bin file, which is specifically suitable for programming the platform flash. The resulting .bin file can now be used with the CH341, a programming software, to download the configuration into the flash memory on the board. Once the .bin file is generated, we move on to the practical demonstration of the experiment on the hardware. First, configure the board for platform flash programming mode by shorting the required jumpers, and then connect the board to the USB port of the PC. Open the CH341 programming software and load the generated .bin file. Program the platform flash using the Auto Program option, ensuring that the Erase, Program, and Verify steps complete successfully. After programming is complete, release the FPGA from reset so that it can load the configuration from the platform flash during power-up. Next, using jumper wires, connect the FPGA GPIO pins to the LED connector on the board. Once powered, observe the LED indicators toggling on and off, which confirms that the FPGA has successfully loaded the design and that the GPIO logic is functioning correctly. This practical demonstration verifies the entire design flow, starting from Verilog code development, synthesis, configuration file generation, flash programming, and finally, real-time hardware operation. With this, we come to the end of part 2 of this video series on the FPGA development board. In this part, we covered the complete workflow starting from Verilog code development, pin assignment, synthesis, and generation of the platform flash configuration file, followed by programming the flash and verifying the design on actual hardware using the LED toggling experiment. This step-by-step process demonstrates how a design moves from software to working hardware on the FPGA platform. In the next part of this series, we will build on this foundation and cover additional practical experiments, including more advanced GPIO usage, clocking concepts, and interfacing examples. If you are following along, make sure your development board and software setup are ready, as the upcoming experiments will be entirely hands-on. Thank you for watching, and we'll continue with part 3 in the next video.